ChatGPT solved the arrays and hash maps LeetCode problem in 3 seconds. Clean code, optimal complexity, edge cases handled, big O analysis included. So what exactly is your job now? Here is what it did not do. Look at Zepto's inventory system, 10 million stock checks per day, and say hash map, not array, because the 2 millisecond latency budget makes a linear scan physically impossible. That judgment call made before any code is written is the one that kept Zepto's system from collapsing. After this video, you will be able to make it and explain exactly why. That is the skill that survives. 5 things you will own after this video. Why an array collapses under Zepto's load. With exact numbers, not theory. How a hash map gives big O of one access and why the space trade-off is trivial at Zepto scale. The exact Redis implementation, HSET, HGET, HINCRBY, and the atomic operation that prevents two customers from grabbing the same last unit. The trade-off AI misses when asked to design this, and the survival skill naming the constraint before naming the structure. If you watch this video to the end, you will be able to answer an arrays and hash maps interview question better than 99% of candidates who have been building software for years. Let us start with what breaks. Imagine finding a specific word in a massive dictionary by reading every single page from A. That takes forever. That is exactly how an array works for inventory lookup. Zepto has 10,000 products per dark store. To check if milk is in stock, the system reads from the first item to the last, one by one, until it finds the match. We call this big O of n linear scan. With 50 users browsing simultaneously, the system runs 500,000 comparisons per second before a single order is placed. The API gateway routes to the order service. If the order service uses an array, it loops from index 0 to index 9999 for every single request. Every customer browsing triggers a full loop. At Zepto's traffic, 50,000 concurrent users during peak hours. The order service is running 500 million comparisons per second. For inventory, before a single rupee changes hands. Worse, the array lives in PostgreSQL. Every browse fires a full table read. At 10 million daily orders, checkout alone generates 100,000 inventory reads per second. Each one is a full table scan. PostgreSQL collapses. The array approach breaks at Zepto scale before you add any other feature. This is the problem that forces a different data structure. Not because arrays are bad, because the 2 millisecond latency budget and the 10 million daily check scale make big O of n physically impossible. That constraint is the entire reason for everything that comes next. Instead of reading every page of the dictionary, imagine having an index at the back that tells you the exact page number. You look up milk, the index says page 4247. You flip directly there. No scanning, no looping. That is a hash map. A hash function takes your key, inventory store 17 SKU4521, and calculates the exact memory address where the value lives. Lookup, insert, delete all big O of 1. Constant time regardless of how many items are in the store. Now here is the part most engineers do not pause on. At Zepto scale, big O of 1 is not just faster than big O of n. It is the only answer that fits inside the 2 millisecond latency budget. Big O of n at 10,000 items takes 18 milliseconds. The SLA allows 2 big O of n is not slower. It is structurally impossible. 3 operations. HSET writes a key value pair. HGET reads it. HINCRBY decrements it atomically. All big O of 1. The HINCRBY is the critical one. It is the operation that prevents two customers from grabbing the same last unit of milk at the same millisecond without needing a database lock. Collision handling keeps the amortized cost at big O of 1 as long as the load factor stays below 0.75. Redis manages this automatically. Hash maps trade space for speed. Big O of n memory for big O of 1 time. At Zepto, 400 dark stores times 10,000 SKUs equals 4 million keys. Each key is roughly 30 bytes. Total 120 megabytes in Redis. For a system that processes 10 million orders a day and generates crores of rupees in revenue, 120 megabytes of RAM is not a trade-off. It is free. That is the constraint-based reasoning that separates a developer from an engineer. The developer sees extra memory. The engineer sees trivial cost for the only structure that fits the latency budget. Now, how does Zepto actually wire this up in production to guarantee that 2 millisecond read? Let us look at the code. Zepto stores inventory in Redis as a hash. The key is inventory store underscore ed skew underscore id. The value is an integer, the current stock count. HSET writes the count when inventory is refreshed. HGET reads it on every browse and checkout. HINCRBY decrements by 1 atomically on purchase. No database lock, no mutex, no transaction. Two concurrent checkouts for the same last unit are serialized by Redis itself. One sees count 1 and decrements to 0. The other sees 0 and is rejected. That is the design decision that eliminates oversell without adding any locking overhead. Customer tabs. Checkout. The app sends a post to the API gateway. The gateway checks the auth token and request rate. Both pass. The request is routed to the order service in under 1 millisecond. The API gateway routes to Redis directly for the inventory check. The order service reads the stock count. One Redis command HGET inventory 17,4521. Redis answers in under 2 milliseconds. Count is 42. The order proceeds. 0 SQL, 0 table scan, 0 latency budget consumed on database I/O. If this kind of judgment call picking Redis HGET over SQL query because the 2 millisecond budget demands it is what you want to make, confidently subscribe now. Every Saturday, one DSA judgment call free. Interview trap. In an interview, when asked about inventory lookup, do not just say use Redis. Say HGET inventory, store ID, SKU ID 01 under 2 milliseconds because the SLA eliminates SQL. Name the command and the reason. Redis executes HINCRBY by -1 atomically. This is the operation that makes concurrent checkout safe without a lock. Two customers adding the same last bag of rice at the same millisecond. Only one succeeds. The first HINCRBY sees count 1 decrements to 0. The second HINCRBY sees 0 and returns a rejection signal. No transaction, no lock, no race condition on a cache. Miss a product not yet in Redis. The order service reads from PostgreSQL and writes the result back. This is cache aside pattern. The Redis hit rate must stay above 99%. If it drops, every miss hits PostgreSQL and the latency budget collapses. That maintenance of the hit rate is an operational judgment AI cannot generate. So when an interviewer asks you to compare these two structures, what do you actually say to prove you understand this? Let us look at the trade-off table. Array lookup is big O of n with 10,000 items per dark store. A full scan takes around 18 milliseconds. The Zepto inventory SLA is 2 milliseconds. Array is not slower, it is 8 times over budget. HashMap calculates the exact memory address from the key and jumps directly. 2 milliseconds always. That is not a performance difference, it is a correctness boundary. At 10 million daily inventory checks, 100,000 reads per second hit the storage layer. An array in PostgreSQL means 100,000 full table scans per second. PostgreSQL collapses under this load. Redis with 4 million hash map keys handles 100,000 reads per second at 120 megabytes of memory. The database is never touched during normal operation. On checkout, two customers might grab the same last unit at the same millisecond. An array in PostgreSQL requires a transaction lock. Select for update, which adds 50 milliseconds and creates a serialization bottleneck. Redis HINCRBY is atomic. No lock, no transaction. Both concurrent operations are handled in the same 2 millisecond window. Zero overhead. This is the design decision that eliminates oversell without slowing down checkout. Ask an AI to implement Zepto's inventory check and it generates a SQL query. Correct result. Correct logic. 8 times over the latency budget. AI defaults to correctness. The engineer defaults to constraint. That gap is the judgment call this entire video exists to teach. The answer is not hash map because it is fast. The answer is the 2 millisecond budget and 10 million daily checks make every alternative impossible. That answer is the one that gets you hired. You have seen the trade-offs and the architecture. Let us put it all together one final time. The full system in one clean view. Full system. Every component visible. 6 hops, 0 SQL queries, total time under 2 milliseconds. Here is the complete path from tab to in-stock badge. And the exact reason a hash map is the only structure that makes this possible. Customer tabs dairy, 50 SKUs. The app sends get inventory to the API gateway. The gateway authenticates the request. All pass. The 50 inventory checks are about to fire, and not a single one will touch PostgreSQL. API gateway routes to the order service stateless. Any of 50 servers can handle this request. The order service has one job here. Fire 50 HGET commands to Redis in one pipeline round trip. Order service sends 50 HGET commands to Redis in one pipeline round trip. Redis processes all 50 in sequence, answers in under 2 milliseconds total. Each HGET is big O of 1. No SQL, no scan, no loop. Compare this to the array approach. 50 SQL full table scans, 500 milliseconds minimum. Database CPU at 100%. Hash map wins by 250 times. Not faster, structurally different. Redis returns all 50 stock counts. Order service maps each count to in stock or out of stock. 0 PostgreSQL reads everything was in the hash map. The Redis hit rate is above 99%, meaning PostgreSQL is contacted less than 1% of the time only for cache misses. That operational discipline is as important as the data structure choice itself. Order service returns the inventory data to the API gateway. Under 2 milliseconds elapsed, 50 badges resolved. The gateway forwards the response to the customer's app. Customer sees 50 in stock or out of stock badges rendered in under 2 milliseconds, 6 hops, 1 Redis round trip, 0 SQL queries, big O of 1 per key. Before this video, the answer to why does Zepto use a hash map for inventory was hash maps are fast. After this video, the answer is the 2 millisecond budget and 10 million daily checks make big O of n linear scan impossible. 4 million keys at 30 bytes each is 120 megabytes trivial for Redis. HINCRBY atomic decrement prevents oversell without a lock. That is the only calculation that matters. That shift from it's fast to the constraint forces it is the judgment call that no AI prompt can generate. That shift is your job. You now own the architecture. Last piece. How do you walk an interviewer through this in 45 minutes? That is next. 45 minutes. Blank whiteboard. Most candidates start drawing immediately. That is the first mistake. Phase 1 is clarifying constraints. Ask for the read to write ratio and latency budget before you even mention a data structure. Phase 2. Propose the naive approach. Say out loud that an array scan takes big O of n and run the math to show why it collapses at scale. You must prove you know why it fails. Phase 3. Introduce the hash map. Explain how big O of one access completely removes the loop and meets the 2 millisecond latency budget. Phase 4. Concurrency. The interviewer will ask what happens if 2 people buy the last item. Your answer is Redis HINCRBY for atomic decrement, no database locks required. Finally, phase 5. The trade-offs. Acknowledge that the hash map requires big O of n space, but quickly dismiss the 120 megabytes of memory as trivial compared to keeping the system online. Before this video, hash maps are fast. After this video, the 2 millisecond budget and 10 million daily checks make big O of n impossible. Hash map is not faster. It is the only structure that fits. The engineer who can say that in an interview, in a system design discussion, in a code review, that engineer is the one who built the inventory system. Everyone else wrote the HGET implementation after the decision was made. That distinction is your survival skill. Next Saturday, linked lists and LRU cache. Redis has a memory limit. When 4 million keys fill it up, something must be evicted. The question is, which one? The least recently used item, LRU cache, is a doubly linked list plus a hash map, both O1. Redis uses it, and here is what AI gets wrong. When asked to implement an eviction policy, it reaches for a sorted set or a timestamp query. An engineer reaches for a doubly linked list because the order of eviction is the correctness guarantee, not an optimization. That is episode 2. The data structure that keeps Zepto's cache correct when memory runs out. Subscribe to ByteLearn for the complete One Engineer System DSA edition. One data structure per week, one Zepto constraint that forces the choice every Saturday. If you are a B.Tech student, a fresher, or an engineer wondering what the point of learning DSA is now that AI can grind latent, this series is the answer. Hit the bell. See you Saturday. Question: which DSA judgment surprised you most? The constraint that forces hash map over array? Drop it below. I reply to the first 10.